Hello, today we'll discuss about radiography or different medical imaging techniques. One of these medical imaging technique includes X-ray machine. So, what are the different medical imaging techniques we are using that we'll discuss as introduction. Now, as we know, this medical imaging is a technique and the process of imaging the interior through which the interior of a body for clinical analysis and medical intervention, as well as we can visualize and represent the function of some organs or tissue. So this is all about your actually this process, this medical imaging technique, this process, they help us to to analyze the physiological changes or activities without uh, without the medical interventions, or we can say that it these are some non-invasive method. They are non-invasive. Okay, so these are non-invasive. Now we have different ways, or we can have this diagnostic. They have different modalities, they have their anatomical regions and different clinical conditions. Depending upon that, we can use different technologies. The first one we can say X-ray technology, that we normally known as radiography or radiographs. Similarly, this technology which uses the X-ray as energy source for imaging, it also includes mammography, then fluoroscopy, angiography and computed tomography, where X-ray is used as the source of energy. Okay. Then we have other ways, other energy sources we can utilize for imaging, that is your ultrasound. And next one is MRI, magnetic resonance imaging, where this is all these three are actually they are taking the images through this or they are under this anatomic regions, they are under this anatomic regions, but some of the cases in ultrasound that also coming under this physiological activity, it can be recorded or the images can be taken. Similarly, this MRI, it includes anatomic activity, physiological activity and also some about metabolic activities. And for molecular level, we have another ways of imaging, that is your nuclear medicine or PET and CT scan, PET CT scan. So these are different ways or technology, imaging technology we are using for in case of your medical diagnosis process. Okay. Now next one is, whenever we are using different frequency, different energy sources, what are the frequency ranges? Now you mark this MRI, that includes your MRI, it is following the frequencies around in a megahertz range. So it is a radio frequency. Then this spectrum shows how the frequency increased and where this X-ray come. So you can find here radio waves. After radio waves, the higher frequency range is microwaves. Then we have ultrasound is somehow lesser frequency. Then we have infrared, then visible range, then ultraviolet. After ultraviolet, we have this X-ray frequency range. They are in the order of 10 to the power 16 or 10 to the power 19 hertz. Then finally we have this gamma rays. So as the frequency is very high, in case of your X-rays, they can penetrate through different parts of our body, different masses and bones, for creating these images. Now these radiographs or X-ray. So you mark, we have the generation of this X-ray through just similar to a cathode ray tube. So you mark here, this is one tube or X-ray generation machine, where we have this side you have a cathode and this side we have the anode. This cathode, they are actually generating electron beam when heated, or we call that thermo-ionic emission, or in some cases we can also provide high potential, so that it can also be electrostatic emission. So in this case, X-rays are a form of electromagnetic energy. It is formed when high speed electrons bombard a tungsten anode target, which is placed here. This is your tungsten anode, you can mark. And like light energy, these useful rays have properties of waves as well as particle. They are duality in nature. They have both particle wave nature. So this X-ray machine or this X-ray tube which generating the X-ray beam, this cathode is heated up to 2200 degrees Celsius, and this tungsten, after once it has been heated, this cathode, they start emitting electrons, and those electrons will travel through this vacuum, and that will be collected, heated this, or that will hit the target of, that is your anode. So this anode is also made up of some different metals, like in this case it is a tungsten anode. So once it has been heating this, when this high speed electron beam is hitting the anode, they will generate some electrons, so they will generate some beams, and that frequency, those energy beams, that will fall in the frequency range of X-ray in the electromagnetic spectrum. So this high voltage, that is around 15 to 150 kV, accelerates electron from the cathode to the anode. When the electron strikes the anode, the characteristic X-ray are produced due to this bombardment, because these high speed electrons, they has to lose their energy by transferring those energy to some other particle, and now they are radiated through this energy has been radiated in the form of electromagnetic waveforms, and that is falling in this X-ray waveform frequency range. So X-ray is generated. Now there is a slit like thing, or this is your glass through which, or filter through which the beam will coming out of this shielding, because as these are very high frequency, they can ionize or these are hazardous for the human being in some cases if it is exposed for a longer time, a longer period. So for that, this arrangement or this tube has to be kept inside a lid box, which is acting as one seal to the X-ray. So only a small exit port is there through which the X-ray beamer travel out. And this X-ray, it is discovered in 1895 by Röntgen. Okay, and now after 1895, in 1896 it has been used for clinical purposes. Now we'll see how this X-ray principle imaging technique works. Now we can mark here the X-ray machine uses X-ray for imaging. We know that this X-ray can penetrate through different parts of our body. It can penetrate to the soft tissues easily and absorb by the denser areas like bone. So depending upon the density or depending upon this mass, atomic mass of these atoms which comprises the body mass at different areas of our human being, the X-ray will be absorbed or it can be transmitted, or it will allowed to be transmitted. So then the X-ray are produced by accelerating electron at high velocity towards a target. Now this is your man or the patient who is lying on this photographic film over this grid system, and then image receptor. This is the arrangement, or we can say it is a film photocell. When the electron hit the target, most of their kinetic energy is converted to heat and a small portion become X-ray. Now these electrons which has been generated at the cathode, that will hit the anode, and most of the cases it will be absorbed by losing their energy, and out of that some of the part will be converted to X-ray formation. Also efficiency is very less. So the basic principle enables X-ray imaging by distinguish between soft and dense tissues, because we have different ions and different atoms at different areas. So they have different atomic masses, and as they have different atomic masses, their properties of absorption of X-ray is also different, and as the absorption property differs, we are getting different contrast images on this photographic film. The partial and complete passing of radiations through the object tends to form an impression of the internal structure of the object on the film, which is placed behind the patient. The black area of the film, once it has captured this transmitted X-ray from the body or through the patient, that is soft portion, because through the soft portion absorption is less, so more amount or more intensity X-ray will be passed through that. So we are getting black areas, and the white area dense region, because or bones, because through this white area means more amount of X-ray has been absorbed at that area or through those portions. So though they which has higher density like bone. So this is your simple block diagram of our X-ray machine. So we have the main supply here, we have some high voltage come, then this we have timer for exposure, how much time we require to expose, it can be controlled. We have some current control circuit, then all these things will be connected to rectifier, which will pass that to a ammeter. Then through this we have to hit the cathode at this point. This filament supply and temperature control is connected to the cathode, and in this side we have the anode, and after this the target, the electron beam will hit this, and after absorption and some of the energy will be radiated as X-ray tube through this slit or through this filtering. So now you mark in this particular X-ray machine, this is one important block, that is your collimator. Collimator is actually it is limiting the X-ray exposure. So it plays one crucial role in case of your image formation and X-ray exposure. A high voltage generator supply the essential power to X-ray tube, as we have seen in the previous slide. A collimator shapes and restricts the X-ray beam to a specific area, because a collimator means it has different types of plates, and once we have this X-ray is coming, and how it will be when these X-rays are coming, how they are be arranged, or what should be the shape of the exposure, it can be decided by this collimator, minimizing the unnecessary radiation exposure and improving the image quality. It typically uses lead sorters. So these are, as we have shown, as I have shown here, these are the lead sorters or blades that can be adjusted to define the size and shape of the beam before it reaches to the patient. So collimator plays a crucial role for quality image improvement or production. X-ray exposure is precisely controlled by an electronic timer and can be automatically stopped using a photo timing circuit. The operator set radiation parameter from the console. There is one operating console from where the operator can set what should be the time exposure, time of exposure, what should be the intensity, what should be the voltage to produce these electron beams. Everything can be controlled. An image receptor below the patient records X-ray image after X-ray passes through the body. Then patient anatomy affects X-ray intensity, tissue absorption and transmission determine the two-dimensional intensity pattern captured by the detector. Then diagnostic image receptor that is present in the photographic film, and this photographic film, above that photographic film we have grids, different grids, and these grids are, they are actually passing these beams in such a manner that the image quality will be enhanced. So that is the grid which is present over this photographic film or array of these cells with phosphorus screen. This photographic film, they have phosphorus screen. We can have some storage phosphorus screens, or we can also directly read it out through digital screens. So these are all about this machine. Now we'll see some of the properties. Now you mark, we have the higher atomic number of the matter, the more the X-ray will be blocked. So atomic number more means it has more density more, so it will absorb more X-ray, and as it is absorbing more X-ray, so it will block it reaching from the film. So we are getting white areas on this photographic film or the image. So some cases you can mark metal bright white, because metal, in case of metal, it will you can say it will very dense, so nothing will pass through it, and or no X-ray beam will pass through it. So we are getting bright white. If we have some minerals, then still they have some absorption, so we are getting white. Then fluid soft tissue gray, if it is fat then dark gray, and if nothing will be there then it's black. So everything, every X-ray, all the X-ray beam will pass through it. So now you can mark, we have a relative intensity versus electron photon energy, that is in terms of kilo electron volt. So as we increase, go on increasing the photon energy, that is your X-ray, how this intensity will be affected. You mark X-ray generated within anode. If it is generated, then once it is leaving the anode, gradually it starts falling, leaving the tube, again some portion will be absorbed. These two peaks, here you can mark these two peaks we are getting, they are the characteristic radiations. Actually we want that this should be captured, this peak and this peak, through this processing of image. So then after the filter we have these peaks, and when it is, this is passing through the body, your patient is lying there, this is passing through the body, then this is your intensity after absorption, this is which is leaving the body. So this intensity will be absorbed in the photographic film and we can get the images. So here you mark one thing, this is the range, ideal range you can find in this between around 50 to 80. In between that we have the two characteristic radiations for imaging. So this is the ideal range of this intensity. If X-ray interact, they can absorb or scattered from X-ray beam. So when the X-ray is passing through different masses of our body like bone, fat, tissue, like that, so they undergo three different processes. They have either scattered or they has been your absorbed. So in this case you mark, we have a Compton scattering and another one is coherent scattering, or it is your Thomson scattering. Scattering means, let's say this is the nucleus and these are the atoms, these are these electrons, they are moving, revolving around this. When this X-ray will come, they will hit this electron and somehow they will move in other direction. This and another particle will be produced. In this manner, it is your inelastic collision. If inelastic collision will occur, then this is your Compton scattering. If elastic collision will occur, that is your coherent scattering or your Rayleigh scattering or Thomson effect. And in some cases, if some energy will be absorbed, then it is called photoelectric effect of absorption. So these three actually affect how much energy or how much X-rays are absorbed while passing through the body or tissue. So these three graphs you can see, one is for photoelectric absorption, another one is Compton scattering, another one is Thomson or Rayleigh scattering. So Rayleigh scattering is less in this blue color line, it is less, significantly less, so we are not considering this. Basically these two, photoelectric and Compton, they are falling in this region. So they are affecting, basically they are affecting the image quality. Now interaction of X-ray with tissue. As we have discussed, different contrast of tissue, the contrast can be formed from due to the absorption and scattering effect in through that tissue. The contrast between this tissue in X-ray images result from varying degree of X-ray attenuation as they travel from source through the body to the detector. Let's say this is the X-ray source which has a intensity of I naught, and when it is passing through the some body mass of width x, and then after passing through that the intensity reduced to Ix and it has been captured in the photographic film. So if we consider that as a monoenergetic X-ray beam has intensity of I naught photon per second per centimeter before absorbed and intensity Ix after passing through x centimeter of absorber, this is a body mass considering, then the linear attenuation coefficient, LAC, we call that linear attenuation coefficient, how much amount of intensity has been reduced due to this absorption, that is defined using one term mu. So this attenuated intensity and the initial intensity, they are related through this parameter, that is your linear attenuation coefficient, that is Ix equals to I naught into e to the power minus mu x, where mu is the attenuation coefficient, x is the distance travel or the width of that mass through which the beam has been passed. This is known as Beer-Lambert law. The absorption, how much wave or beam has been absorbed through this mass, can be defined from this equation, that is A is equals to log or ln, you can say log 2 here, log 2 or ln L0 by I0 by Ix. I0 means it is your initial intensity, Ix means after passing through that mass. So this will give you, this ln I0 by Ix will give you the absorbance. The linear attenuation coefficient is related to half value layer. We will see what is half value layer. Some X-ray pass directly through the tissue without interaction. This is called primary radiation. X-ray that scatter and change direction within the body produce secondary radiation, which can decrease the image clarity. And this occurs due to this type of Compton and Thomson effect. Scattering. X-ray completely absorbed by the tissue do not reach the detector and formed absorbed radiation. Absorbed radiation, you are getting white picture, or on the picture you are getting white areas. This differential attenuation is fundamental for distinguishing tissues in radiographic images. So now what is LAC? As we have discussed, it is a linear attenuation coefficient, and this effect is a combination of how this mu coherent, mu Compton and mu photoelectric. They have different, and basically these two they have significant role, and this is a very less amount. It adds very less amount of mu attenuation. So combiningly we can say this mu can be written as, this linear attenuation coefficient is ln I0 by Ix divided by the x, which is the thickness of that mass. This is the mass thickness through which this energy has been passed. This is your I0 through this mass, X-ray has been passed, and we are getting the intensity of X-ray after passing through that, that is Ix. Okay. So this is all about the linear attenuation coefficient. Now coming to the half value layer. The half value layer is the thickness of material required to reduce intensity of radiation like X-ray to half of its original value. Whatever may be the value, that is, let's say I0, if it is reduced to half of its value, then what should be the thickness of that material to reduce that? It is a key concept of radiation shielding and beam quality assessment. So this can be written as HBL equals to your 0.693 divided by mu. So this will give you, mu means your attenuation coefficient. So this will give you the half value layer. Basically it is influenced by the material and radiation energy. Here you can mark at different energy levels, if it is a 30 kilo electron volt or 50 kilo electron volt or 100 or 150 kilo electron volt for a muscle, and for different mass length, this is your x means length, material, how much material. So if 30 kilo electron volt is passed through any mass of this muscle mass of 1.8 centimeter, then it will reduce to half after passing through it. Similarly others are there. So these are the HVL values determined at different energy levels for muscle, for bone. So you mark this bone, let's say it is 0.4 centimeter only, means 0.4 centimeter bone is sufficient to reduce this is 30 kilo electron volt to half of its value. So this is, but whereas the muscle it is 1.8 centimeter, that is because muscle is less denser than bone. Now coming to the numericals. Question is, what fraction of 140 kiloelectron volt X-ray incident upon 0.5 mm, means X is given 0.5 mm, thick lead apron will be transmitted. What fraction of 140 kiloelectron volt X-ray incident upon a, when this is, let's say this is your 0.5 mm thickness apron, lead apron. From here you are passing this X-ray that is of 140 electron volt. Then what is the percentage it will pass through it. Then to get that, another given thing is there, the mass absorption coefficient for lead at 140 kiloelectron volt is given as 2 centimeter square per gram mu m, and density of lead is given as 11.3 gram per centimeter cube. Now what is this particular parameter? That mass attenuation coefficient or mass absorption coefficient is defined as, that is mu m, it is your mu by p. So they are given in centimeter per gram, centimeter square per gram. So this mu m, as we have discussed, it is the combined value of your attenuations in case of coherent, Compton and photoelectric divided by its mass, density, that is your rho, that will give you mu by rho. Okay. Now coming to the solution. So we can compute the attenuation coefficient by just multiplying these two values, because it is given mu m, that is your mass attenuation coefficient or mass absorption coefficient is given, and this rho is also given for lead. Now we found that 23 per centimeter, this is your attenuation coefficient. So at 140 kiloelectron volt, so 23 per centimeter is the attenuation coefficient for of the X-ray at 140 kiloelectron volt X-ray. We then use this exponential fall of X-ray to find out how many X-ray will be transmitted through the apron. So we know that simply you multiply this. So X is given, X equals to 0.5 millimeter, that means 5 into 10 to the power minus 2 centimeter, and we know what is mu value, we know what is X value. Then we can easily calculate, and you also know what is I naught, and we need to calculate what is Ix. Okay. So this is the thing we need to calculate. So using this formula, I equals to I naught e to the power minus mu x, as we have calculated, this is your mu is found to be 23, so that is your 23 per centimeter inverse. X is your 0.5 millimeter, that is your 5 into 10 to the power minus 2 centimeter, and this is your value. So we are getting this value Ix equals to I naught into e to the power minus 1.15. So we can easily calculate how percentage, what is the percentage. So here this value is equals to Ix, as we have calculated. When you calculate this e to the power minus 1.15, it is equals to 0.3 I naught. So Ix is equals to 0.3 I naught. What does it mean? That means 30% remaining, means 30% will be we are getting as the output once it has been passed through that. So that means 70% of the X-ray has been absorbed by the lead apron. Only 30% has been passed through it. Second question, an X-ray beam is of initial value I naught of 70 kilo electron volt imaging the chest is assumed to undergo attenuation through the muscle tissue for thickness. Muscle tissue, this is muscle tissue, let's say M, of thickness 16 centimeter, and further through the bone tissue of thickness 4 centimeter. Means here we have two different layers. One is muscle, another one is bone. From this side the intensity is I naught, it is passing through M, then we are getting here I1, then I1 is the next, or it is the initial value for the passing through this bone, and finally we are getting the output as I2. Are you getting? So that means these are the initial value for this muscle is I naught and final value is I1. Then the final value what we are, the intensity what we are getting after passing through this muscle, that will be considered as the initial value for the bones, and again it will pass through the bones. We are getting finally some of the will be absorbed and we are getting the final value I2. So this is the process we need to calculate. And now the half value layer of thickness of the muscle and bone are 3.5 and 1.8 centimeter respectively at 70 kilo electron volt. 3.5 for muscles, 1.8 for bones. That means half of the energy will be absorbed at this 3.5 centimeter of muscles and 1.8 centimeters of bones. Then percentage of X-ray intensity transmitted through the body is dash. So we'll see that. So first we know that this is the formula. Then we need to calculate that what is the value of half value layer. Formula we know that mu equals to ln2, because you have this ln, your that value we have to calculate means mu x. So in the previous, as we have seen, here you can mark here mu can be equals to ln I naught by Ix divided by x. Okay. So from where we can calculate SBL equals to 0.693, which is nothing but ln2. ln2 is equals to 0.693. So this value we already know. Now we also know what is the values of mu. So mu can be calculated from the HBL values. HBL values we have previously seen that HBL for muscle is 3.5, HBL for tissue bone tissue is 1.8. So we can easily calculate what is the attenuation coefficient for muscle, what is the attenuation coefficient for bone. That has been calculated as 0.198 centimeter inverse for your muscle, and 0.385 higher than this muscles. For bone it is 0.385 per centimeter. Now as we know the attenuation coefficients, then we can use this formula. So two layers as we have discussed. First layer muscle, second layer bone. This is your I naught. This is, let's say, after passing this at this point I am getting I1. So this I1 will again moving through this bone and I am getting I2. Okay. So this is your final value. So we know this muscle, for this it is mu m, for this it is mu v, and we have this formula. So we'll see for the thickness for this first layer of muscles, it is of 16 centimeter. Eye muscles can be found, that is your I naught e to the power, this is the attenuation coefficient into 16. Then once we get the eye muscle, it is the initial value for this eye bone. So eye muscle into e to the power coefficient, attenuation coefficient for bone into 4 is the thickness of the bone. Then finally we get the value, that is I naught. This value is calculated, this value we have calculated to be 0.042. We put that value here, 0.042, and this value, this is 0.385 is the attenuation coefficient of bone, 4 is the thickness of the bone. Finally we are getting this eye bone equals to I naught, means after passing through these two layers, muscle and then bone, we are finally getting the intensity of is equals to this much. The total percentage of X-ray intensity transmitted through the bone is this one. So now which is can be calculated by taking the percentage. So if we can consider, implies this eye bone divided by this I naught is taken this side, so it is equals to I naught. So you are getting 0.042 into this value, into this value here. So we are getting, it is almost around 0.009. If you take the percentage, then it is 0.9%. So only you mark, only 0.9% of the initial value of X-ray in that intensity has been passed through the or transmitted through the body, and this will be absorbed or captured by the your photographic film for image creation. Thank you. Next class we will see the mechanism for computed tomography.